Alright, so let's start talking about are all atoms equal? The quote that we have here is great minds discuss ideas, average minds discuss events, and small minds discuss people. That's from Eleanor Roosevelt. And so we're going to talk about are all atoms equal? Are all atoms the same? So what we're hopefully trying to learn here is that students will understand the process by which ions form. So we're going to talk about ions, how they form, differentiate between atoms, ions, and isotopes, and then calculate the average atomic mass for an element. So we're going to discuss these three things. What we should already know is that atoms are made of protons, neutrons, and electrons. And experimental evidence led to the development of the current model. So we looked at the experimental evidence previously in models of the atom, and we saw that experimental evidence that build us up to the atomic model that we have. What we learned in the lab, that beings, like atoms, can vary in mass. So not all beings are the same mass. They're all beings, but no, they're not all the same mass. And that the average atomic mass is determined by finding the mass of a large sample of atoms. So when we're looking at a sample and looking at average atomic mass, we look at an entire large portion of it, and then we break apart and find its different pieces, just like we did with the beans. And looking at this, now we talked earlier about Thomson and how Thomson discovered the electron, but an extension on Thomson's experiment with neon led to two different neon lines, and you kind of see them down here, all the way down there. And these lines could not be understood by our model of the atom. Why were there two different neons in the sample? Now, all these other lines out here are just contaminant. So everything up there is contaminant, but they saw the two neon lines of where they're supposed to be. And with the current model of the atom, with protons, neutrons, and electrons as they existed, it couldn't be understood. So what it led to is it led to isotopes. Now what an isotope is an element that has the same number of protons, the same number of electrons, but different numbers of neutrons. So all versions of that element have all these things. There are some expressed in hyphen notation. You can see this down here where you relate it to helium-4 or helium-3. And we can see by looking in the nucleus, we see that we have 4 particles in this nucleus. And then in our other nucleus, what we can see is that we only have 3 particles. And so what we see is those are going to be our two nucleuses. They're both going to be helium because they both have 2 protons. But the difference between this is the number of neutrons. In our helium-4 we have 2 neutrons. In our helium-3 we only have 1 neutron. So when we're looking at this, the way that we can differentiate between just a regular helium, helium-4, and a helium-3 is we use what we call nuclear symbol notation. Now, to write nuclear symbol notation, it's similar to hyphen notation but a little different. Okay, nuclear symbol notation, we identify the number of protons to determine the element. So we look at the protons and figure out what element it is. Then we write down the chemical symbol for the element by looking on the periodic table. So if we have, in this case, we look and we see that we have 2 protons, that means that we're dealing with helium. So we write down the chemical symbol for helium. Then we write down the atomic number on the bottom left corner of the chemical symbol, and you can see that it's right there, and it's also right there. And then we write the mass number on the top left corner of the atomic symbol. And your mass number, what this is that it's just your protons plus your neutrons. So that's where we get helium-4 and we get helium-3. So that's how we write our nuclear symbol notation. So let's look at this, our fundamental question. We see which of the following is the nuclear symbol notation, and we know that this would be our nuclear symbol notation, and this guy over here, that is hyphen notation, representing the same thing, but just different types of writing it. So, jumping into our next question, we see we have a proficient level question. It says, write the nuclear symbol notation of an element that has 8 protons, 8 neutrons, and 8 electrons. So the first thing we do is we look at the protons. We have 8 protons. So we look on our periodic table and we see that the atomic number of 8 is represented for oxygen. Okay. Now, we take that and we write the atomic number down there. And then what we do is we see that we have 8 neutrons. So remember what the mass number is. The mass number is protons plus neutrons. So 8 plus 8 is 16, and we write it right here. The last thing that we can check is we have 8 electrons. So we do not have a charge if protons equal electrons. So protons equal electrons here. We just write it like this, and that is our nuclear symbol notation for oxygen. Our next one, it says on this one, how many protons, neutrons, and electrons are in the following atom of potassium? So when we're looking at this, what we can do is we have protons, neutrons, and electrons. So our protons are going to be our atomic number, which that would be 19. Now our neutrons, remember what this number is up here. It's our mass number. It's protons plus neutrons. And this is protons. So if we subtract protons, what are we left with? Just the neutrons. So we look at it and we see that we have 39 minus 19 will give us 20. So we have 20 neutrons, and it's not charged. Like, we don't see, it's not an ion. An ion's where we have a charge. We don't see anything over here, so guess what? We have the same number of electrons as we do protons, and we get 19, 20, and 19. Now, when we're looking at charge, when we're talking about those ions, charge can be added to nuclear symbol notation, and all we do is we add it out here. Okay, and what we do is we take the number of protons and subtract the number of electrons. That's how we find charge. It's protons minus electrons. So protons minus electrons equals our charge. Okay, protons minus electrons equals our charge. So let's look at another example. It says write the nuclear symbol notation for an atom of iodine. So we have iodine 127, that has 54 electrons. Okay, so it's iodine. We write I for the symbol. And then we look on the periodic table and we see that iodine has 53 protons. And here, this number in hyphen notation, that is going to be our mass number. So we just write that 127 there. Now the trick to this one, remember, it's protons, which is 53, minus electrons, which is 54, which gives us a -1 charge. So all we have to do here is just put a negative, and we can put the 1, but normally we just leave it off, and this would be our answer. Moving on to our next one. It says how many protons, neutrons, and electrons are in the following atom of calcium. So we look at this. Protons, neutrons, electrons. Well, protons, that's right here, 20. And then to find our neutrons, we go 40 minus 20 gives us 20. And electrons, remember what our equation is protons minus electrons equals our charge. So in this case, we have 20 protons minus our electrons, which we don't know how many we have, equals -2. Okay, so we go ahead and we solve for this, and we take our 20 to the other side by basically taking and subtracting 20 from each side, and what we'll get is we get electrons equal -2 minus 20, and that will give us 22 electrons, which should make sense. We have 2 more electrons than we do protons, so it should be a -2. So now that we looked at our nuclear symbol notation and how we write isotopes, we can look at the atomic mass. Now, If an isotope has different masses, what is the mass of hydrogen? So in this one, when we're looking at it, we have three different isotopes of hydrogen. We have hydrogen 1, hydrogen 2, and hydrogen 3. So when we're dealing with hydrogen, just in general, we don't separate it out into hydrogen 1, hydrogen 2, and hydrogen 3. It always exists as a mixture of those three isotopes. But when we're looking at it, it'll exist in a mixture in this proportion. So 99.98% of hydrogen is hydrogen 1, and 0.0115% of hydrogen is hydrogen 2, and 0.0005% of hydrogen is hydrogen 3. And it always exists in these percentages. And so what this allows us to do is this allows us to calculate the average atomic mass. And what this is this is just the mass on the periodic table. So when we look on the periodic table, average atomic mass, that red number is the number below the symbol in the periodic table. That is the average atomic mass. And this is how they got that calculation. To find the average atomic mass, first we change the percent abundance into a decimal, and all we do to that is we take the 99.98% and we move it 2 places to the left, 1, 2. And so all we do here is move it 1, 2, and that's where we get that number right there, the 0.9998. And we do the same thing with all the other percents. Then what we do is we multiply by that isotope's mass, that isotope's atomic mass, in that decimal form. And then what we get is we get the contribution of each, and then all we do is we add them up to get our average atomic mass, which that's the mass of hydrogen on the periodic table. So let's go ahead and let's do an example. So when we're looking at this, all we do is we take our percent and move it over 2 places. So we move it over 1, 2. So this one's going to be 0.05845. And this 1, 2, this will be 0.91754. Move it over 2 places, 0.02119. Move it over 2 places, 1, 2. So 0.00282. Then all we do is multiply each one. So we'll multiply 53.9396127 times 0.05845, and we'll get right around our 3.153, and then multiply here. So multiply those guys, and we will get 51.323, and then we multiply here and we get 1.206, and then we multiply here and we get 0.163. And then all we do is add those guys together, and we will get an average atomic mass of right around 55.845, which, if you look on the periodic table, that is the average atomic mass on the periodic table for iron. Our next one, when we're looking at this, it says, using the data below, determine the unknown element. So we don't know what it is, but we have the atomic mass and we have the natural abundance. So what we do is we go ahead and set this up. Remember, move the decimal, move, move, and move, move. Okay. Now, one way you can set it up in your calculator to kind of save you some time is kind of put it in parentheses. Go parentheses 62.93 times 0.6917 parentheses plus parentheses 64.93 times 0.3083. And if we put it in the calculator like this, we can set it up like this, we can just press enter and we'll get a number which is 63.55. And if you look, that on the periodic table, that is the atomic mass of copper. So this unknown element would be copper.